Swayam Prabha. Digital India. Educated India.
Okay, now let us start with another problem. An urn contains 40 red balls, 60 green balls. What is the probability of getting exactly k red balls in the sample size of 10 if the sampling is done? So, with replacement, without replacement are the two cases. So, the meaning of with replacement is to pick a ball from the 100 in urn note, its color, and replace it and pick again. And this process is continued for 10 times, then the probability of a red ball equal to P, which is equal to 2 by 5, and a probability of green ball equal to Q equal to 3 by 5 with N equal to 10. Therefore, the probability of K red ball in 10 trial is given by Bernoulli of K comma N comma 2 by 5 is N equal to 10, and K you have to choose what size of the red ball exactly, and a 10 CK, the possibilities of P is equal to 2 by 5 and 2 by 5 K, 2 by 5 whole power K into 3 by 5, N is 10, 10 minus K. Without replacement, here we sample the ball and do not replace it in the urn. Therefore, number of ways of getting 100 balls from 10 balls from 100 balls is 100 C10. So, out of these 10 balls, the number of ways of getting K red ball is 40 CK, and number of ways of getting 10 minus K blue ball is 60 C 10 minus K. Since getting K red balls and 10 minus K blue balls are functionally independent, therefore, the total number of ways are 40 CK, and 60 C 10 minus K is using the product rule. Hence, the probability of P of K red ball without replacement is given by P of K equal to 40 CK into 60 C 10 minus K divided by 100 C 10. Now, we have a multinomial distribution. Each of the outcomes EI, I varies from 1 to m occurs Ki I equal to 1 to m times with K1 plus K2 and so on Km equal to n. Now, the probability of K1, K2, Km is given by the multinomial probability distribution. P of K1, K2, Km is Nc K1, K2, Km into P1 power K1 into P2 power K2 and so on Pm power Km. And we have a simplification n factorial by K1 factorial into K2 factorial and on Km factorial into P1 power K1 into P2 power K2 and so on Pm power Km. This also we already explained, and recollecting the definition, and if you put m equal to 2, the multinomial distribution reduces to binomial distribution, and we have to go on one example. A pair of dice is rolled 8 times, right, and we will find the probability that 7 or 11 occurs thrice, 2, 3 or 12, 2, 3 or 12 twice, any pair twice and any other combination once. For each rolling of pair, there are 4 events, E1, E2 and so on E4, and the probabilities are obtained from the table as shown in the below. E1 is either 7 or 11, therefore, probability of E1 is 8 by 36, because pair of dice mean totally 6 into 6 is 36. Here 7 or 11 corresponding, the chances is 8 by 36. Suppose event 2 or 3 or 12 comes, then probability of E2 is P2 equal to 4 by 36, and any pair P3 equal to 6 by 36, and other combination E4 equal to P4 is 18 by 36. So, in the equation 4.33 and substitute K1 equal to 3, K2 equal to 2 and K3 equal to 2 and K4 equal to 1. Therefore, P1, P2, P3, P4 are given by probability of 3, 2, 2, 1, which is equal to 8 factorial by 3 factorial into 2 factorial into 2 factorial into 1 factorial is 8 by 36 whole power 3, and for second even 4 by 36 for 2 power 2 and 6 by 36 power 2, 8 by 36 whole power 1. After simplified, we have 0.003161. So, when m equal to 2, this reduces to binomial. Otherwise, in general 3, 4, it will come multinomial. Now, we have an example. We have a computer software company wants to recruit 5 new engineers. The probability that a person interviewed is given a job offer is 0.7. We want to find the distribution number of probability people interviewed for the 5 position. Now, according to the equation, P equal to 0.7 and K equal to 5. So, probability of E equal to N is N minus 1 C 5 minus 1 equal to 0.7 possibilities of job, and not possibilities 1 minus 0.7 is 0.3. Here 5 position is recruited, therefore, N equal to 5. So, K equal to 5 and based on that N minus 5, and then N varies from either 5th or 6th or something will come, and then we have what shown in the figure of up to 15. So, the mass function can be evaluated. So, the possibilities of the 6th is maximum 0.2521 will come and gradually decreasing, and corresponding there is nullified in the 15th one is a negative binomial, and this is the application related to multinomial and in terms of the binomial also generated. Next, hypergeometry distribution. If probability of E equal to K, and then we have a NCK or KCK here, N minus K by N minus K divided by NCN is known as hypergeometry distribution, and this equation is a summation over all K. Therefore, summation K equal to 0 to N KCK of N minus KC N minus K is NCN. Now, we have an example, Moss megabucks. So, Massachusetts megabucks lottery is played as follows. A player has to choose 6 numbers from a slate of 42 numbers. Twice a week a lottery commission draws 6 numbers. If all the 6 numbers of the player match all the 6 numbers drawn by the commission, the player wins megabucks. So, there are a smaller prizes for matching 5, 4 or 3 numbers. So, we have to calculate the probability of winning the megabucks or the smaller prizes. So, the possibilities of megabucks we calculated like this: K and N of K and C of K and P of K. So, the based on C of K is D of K by N of K, and N of K is the second column is calculated with the help of 6EK into 42 minus K C 6 minus K, and then C of K is D of K by N of K, and the fourth column P of K is the probability of winning, that is N of K divided by D of K. So, this is the meaning of K, N of K, C of K and P of K. So, start from K equal to 0 to 6 because of throwing dice corresponding to this, of winning the K digits. So, suppose it starts with K equal to 0, therefore, 6Z0 is 1, 42 minus 0 is 42, 6 minus 0 is 6, therefore, 42 C6 divided by 42 C6 is 1, Therefore, corresponding this will calculated and C of k is calculated. So, the possibility is 0.3713060035 will come. Proceeding in this way, you start with k equal to 1, k equal to 2, k equal to 3, k equal to 6. So, what happened? When k equal to 1 is 61, and then 42 minus k is 41, 6 minus k is 5, and then substitute it, you have 22,61952 for n of k, and here d of k is corresponding the value of 1 which is equal to 42 C6, that is d of k, and C of k is d of k by n of k, and then we can reciprocate it. This represents the winning, therefore 0.431194,105 will come. Proceeding in this way, we can get up to 6. So, n of k is demonstrated, C of k demonstrated, and P of k identified. So, substituting n equal to 42, n equal to 6 and k equal to 6. So, we have probability of E equal to k, and the results are tabulated for k equal to 0 to 6. So, in this table, the second column is n of k, and the number of way k digits can be formed from 6 digits. In the third column, C of k represents the chance of winning with k digits. Fourth column, P of k is the probability of winning. Next, Poisson distribution. So, Poisson distribution is a limiting case of binomial, and Poisson distribution takes the value of 0 to k. Here mean and variance are equal at random points with the parameter lambda is given by probability of k colon lambda equal to e power minus lambda into lambda power k by k factorial, where k is positive. So, during this certain experiment, the number of alpha particles passing through a sensor in 1 minutes interval is 3.2. So, the Poisson distribution is lambda equal to 3.2 can be written as P of k of 3.2 equal to e power minus 3.2 into 3.2 whole power k by k factorial. So, this is graph in the figure 4.71. We want find the probability that the picture. So, here 6 alpha particles passes through the sensor is given in millisecond, and substitute in this equation lambda equal to 3.2. So, that the equation will be probability of 6 comma 3.2 is e power minus 3.2 into 3.2 whole power 6 by 6 factorial equal to 0.06079, that is, take the value of 0 to 6, and then the probability of this is chances of the idea is in between 0.5 to 1.1. Therefore, the value is 0.061 calculated like this. Based on that, we can identify. Number 2, no more than 3 alpha particle passes through the sensor. Therefore, the cumulative distribution is given by probability of k is 3.2, and substitute lambda equal to 3.2, and what the values range from 0 to 3, we have 0.6025. Next, based on the example, the average number of customers arriving at the service counter in a supermarket is lambda. The probability of k customers arriving in the interval 0 comma t minutes is given by the Poisson distribution P of k comma lambda equal to e power minus lambda into lambda t whole power k by k factorial. So, in the non-overlapping interval 0 comma t1 and t1 comma t, so we can write the following Poisson law: probability of n1 customer in 0 comma t1 and n2 customer in t1 comma t. Therefore, probability of n1 customer in 0 comma t1 into probability of n2 customers in t1 t. So, these two events are independent in disjoint intervals. So, we will find the conditional probability that probability of n1 customer is 0 comma t1 divided by n1 plus n2 customers in 0 t. So, from the definition, the conditional probability we can write P of n1 by n1 plus n2, which is equal to probability of n1 plus n2 divided by probability of n1 plus n2 comma 0 t, and since they are independent, therefore product them. So, it splitted into product, and we know the Poisson expansion of probability n1 comma 0 t1 is e power minus lambda t1 into power n1 divided by n1 factorial. For second term, e power minus lambda into t minus t1 into lambda of t minus t1 whole power n2 by n2 factorial divided by e power minus lambda into lambda t whole power n1 plus n2 by n1 plus n2 factorial. So, we have lambda t1 power n1 into lambda of t minus t1 whole power n2 into n1 plus n2 factorial divided by lambda t power n1 plus n2 into n1 factorial into n2 factorial. So, we have t1 power n1 into t minus t1 whole power n2 equal to n1 plus n2 factorial by t power n1 plus n2 into n1 factorial into n2 factorial. So, this is the meaning of one is a conditional over the other. So, this yields the independent of lambda factorial. Therefore, the Poisson distribution has been used in number of applications such as number 1, telephone call coming into an exchange, number of telephone calls coming into an exchange, number of cars entering in highway ramp, number 3, number of packets transmitted along the wireless lines, number of customer at the checkout counter, number of misprints in the book, number of photons emitted. So, these are all the ideas we have to use in the binomial distribution, approximation of binomial distribution. So, binomial of k over n comma p is equal to nck in p power k into q power n minus k, and the expansion is n factorial by k factorial into n minus k factorial into p power k into q is 1 minus p whole power n minus k. N factorial is nothing but n into n minus 1 into 1 divided by 1 into and so on k into 1 into n minus k factorial. So, cancel up to n minus k. So, the numerator is n into n minus 1 into n minus k plus 1 by n power k, and lambda power k by k n power k, and then n power n minus k into n power k is what n power n, and then we have only k factorial corresponding 1 minus lambda whole power n by 1 minus lambda by n whole power k. So, if n becomes very large for moderate lambda, therefore, the quantity 1 minus lambda by n whole power n can be approximated by e power minus lambda. Therefore, the quantity 1 minus lambda by n whole power k can be approximately as 1. So, finally, if k is much smaller than n and the quantity n into n minus 1 into n minus k plus 1 by n k can be approximated by 1. So, thus binomial distribution can be approximated as b of k colon n comma p is approximately equal to lambda power k by k factorial into e power minus lambda, where k is positive. Next example. A computer system consists of 1000 microchips, and the probability of failure of the microchip is 0.005. So, we have to find the probability of k microchips failing using both the binomial distribution and the Poisson approximation for k equal to 0 to 15. So, we will also find the percentage error between the two. So, using the binomial distribution, k chips failing in 1000 trials given by p of k of 1000 comma 0.005, which is equal to b of k. So, b of k 1000 0.5 is nothing but b of k is here n equal to 1000 factorial divided by k factorial into 1000 minus k into p is 0.005, q is 1 minus 0.005 is 0.0995 the whole power 1000 minus k. Now, using the 4.26, the formula developed with and bk can be solved recursively and replace k to k plus 1. We have 1000 minus k into 0.5 divided by k plus 1 into 0.995 b of k, and simplify, you have 1000 minus k by k plus 1 into 1 by 188 b of k. Now, using the Poisson approximation, if np equal to lambda which is equal to 5 and substitute that, we have the following approximation corresponding by Poisson as well as binomial also we can generate it with help, because np and npq are equal and the k equal to 5 and lambda equal to 5. Therefore, we can easily calculate both binomial as well as Poisson, and compare with Poisson and binomial, we have a error. So, sometimes it may be more or less equal and minutely they changed. Therefore, the percentage of error also showed in the table, and the figure of 4.71 and the graph 4.72 in the next page of the binomial distribution Poisson approximation also picturized, and this figure are closely approximately equal and some more error occurred, and the table of the graph is approximate because was as k is increased, and the approximation is excellent in the vicinity of k equal to 5, about 0.05 minus 0.25 percentage. So, this is the picturization of Poisson as well as binomial, and the error between the Poisson binomial is minute, right. So, next we are going to discuss logarithmic distribution. If the base b is 10, so the generics ln becomes a log, and the probability of the first significant digit d from 0 to 9. So, p of x1 of d equal to log of 1 plus 1 by d, where d equal to 1 to 9. So, this equation is called as Benford law, stated in the 1938. So, the probability of occurrence of the first significant digit is a cluster distribution, and 0 cannot be the first significant digit, therefore, it can be a significant digit only in the first one. Now, we have an example. In a cluster of numbers from different scale factors, we have a occurrence 1 to 0, 1 to 9, and px1 of 1 is log of 1 plus 1 by 1 is log 2, log 2 is 0.3010. Now, we have the first significance is 30%, and it is not a uniform distribution of 11.1%. Therefore, the probability of 2 is 17.6%. So, the probability of other significant digit is shown in the table. So, this they show the 9 as the first significant and the least probability is 4.6%. So, this is a table of a Benford distribution, and it is a realistic example we have taken from the physical constant, and we referred some chapter and tabulated in the significant digit 1 to 9. So, this is a histogram related to Benford function and a normal table also explained, and then we can have the significant from 9 to 0.3 of the y axis, and fd of d is maximum level reached 0.3. Next example, the physical constant have totally different units. So, the probability of significant digits are shown in the figure along with the graph of Benford law. So, the graph is decreasing, start from the 0.3, the corresponding y axis, and x axis 1, mid of 1 is 0.1, 0.5, and it reaches to 9, then the physical constant is 73. Therefore, the table and graph shows the event for a sample of 73. the probabilities follow the logarithmic distribution. See, beautifully decreasing the logarithm function generated, and the reasonably closely except for the number 3. So, in conclusion, in a mixed population of the different scale factor, the probability of digit 1 to 9 are logarithmically distributed and not uniform. That is the surprise result. Now, we have a summary of discrete distribution we come across. So, P stands for success and Q stands for failure. So, P plus Q is 1, and we come across the distribution, they are number 1 Bernoulli, and you have to revisit, and it is denoted by B of P comma Q, P for success, Q for failure, and 0 otherwise. That is in terms of the function, P of P comma Q is P when k equal to 1, if equal to Q, k equal to 0. For the binomial, B of k comma n comma P is NCK, P power k into Q power n minus k, where k equal to 0 to n, otherwise 0. For multinomial, k expanded to k1, k2 and so on km, and then NCK expanded to NC, k1, k2 and so on km, and P power k1, P2 power k2 and so on Pm power km. Here summation of all Kn is equal to n, and summation of all Pi equal to 1. In geometric distribution is G of k comma P is Q power k minus 1, where k varies from 1 to infinity, otherwise it becomes 0. For negative binomial, apply the Pascal triangle. So, n minus 1 C k minus 1 P power k Q power n minus k is generalized of n of P of P, otherwise it becomes 0. For hypergeometry, P of n comma k equal to k C k n minus k C n minus k C by n C n, otherwise it becomes 0. So, this is the meaning of what the revisited of all these things. Remember all this. And one more is Poisson. Poisson is based on what limiting case of the binomial or vice versa. P of k comma lambda equal to e per minus lambda into lambda per k by k factorial, otherwise 0, because here NP and NPQ are equal, and logarithmic Benford B of t equal to 1 by n of log of 1 plus t, where d equal to 1 to 10 power n minus 1, and semi-infinite when theta lies between 0 to 1 and k is greater than or equal to 1, P of k comma theta is minus theta per k by log of 1 minus theta. For semi-definite of logarithmic 2 is P of k comma theta equal to minus of 1 minus theta whole power k by k into log n, where theta lies between 0 to 1 and k is greater than or equal to 1. So, this distribution we have to remember and solve it, so that you can understand the problem related to the mean and variance corresponding to the distribution function. Now, we have a topic, determination of distribution and density function. This also already discussed the theory, and we have to see some more example and corresponding problem. So, a die is tossed and the random variable x is defined by the amount 1, positive mean success and lost mean negative on the face of the die is shown in the table. We have to find the CDF, cumulative density function fx of x, and probability density function f of x. So, we will follow the steps to find the probability function. Step 1, mapping the diagram of 5.2.1 is drawn with the positive numbers indicating win and negative numbers indicate loss. Number 2, from the mapping diagram of the region of x or x is less than or equal to minus 9 and minus 9 x is lies between minus 9 to minus 4 and x lies between minus 4 to 5 and x lies between 5 to 8 and x is greater than 8. So, 5 regions in a different way, the corresponding set Ix on the real line for all the phi region. Therefore, eta is ranges from minus infinity to x. And next step, we will find all the points in the sample space that maps into Ix for every region of x. So, x is less than or equal to minus 9. Since no point in S maps into Ix of the next figure, so we have f of x is 0. In the region of the figure 5.21b, so this is 5.121 A, B, C, D, E. So, please you recollect it, and then x is less than or equal to minus 9, and the possibilities is this: when x lies between minus 9 to minus 5, and then x, the third one is E, C stands for x lies between minus 4 to 5, and D is minus 5 less than x less than or equal to 8, and x is greater than 8, then the picture is like this. So, keep it in mind. So, for B in this region, only 1.3 maps into Ix, therefore, P of 3 equal to 1 by 6, and Fx of x is 1 by 6. If x lies between minus 4 to 5, so the 0.326 from S maps into Ix, hence Fx of x is 1 by 2. If x lies between 5 to 8 in this region, the point S maps to Ix, hence Fx of x is 2 by 3. So, the pips on the die, if 1 and 4 comes, the win or loss is 8, 2.6 is minus 4, 3 is minus 9, 5 is 5. So, this is a pictorial representation of the possibility of winning and losing the game. So, if x is greater than 8 in this region, all 6 points they demonstrated in the figure 5.22, and the entire sample space is explained. So, unit step function we can define as Fx of x of a summation of all 1 by 6 into u of x plus 9, 1 by 3 into u of x plus 4, 1 by 6 into u of x minus 5 plus 1 by 3 into u of x minus 8. So, that the cumulative density function is graphed like this. And step 5, we can now find the density function by differentiating the distribution function, bearing in the mind of differentiation of the unit step in the Dirac delta function, and performing the indicated differentiation is Fx of x is 1 by 6 into delta of x plus 9 and 1 by 3 into delta of x plus 4 plus 1 by 6 into delta of x minus 5 plus 1 by 3 into delta of x minus 8. So, from the figure 5.23 it stands for what? The strength and impulse function and adds to 1. So, the probability density function is shown in the figure of 5.23 to table of 5.22, and following that the picture shows that probability of x equal to minus 4 and corresponding cumulative density function and PDF also explained, that is Fx of x is minus 4 minus Fx of minus 4 is 1 by 2 minus 1 by 6 is 1 by 3 will come. So, we have successive inequalities of the range varies from minus 5 to 4 and minus 4 to 4, and x is less than or equal to minus 4. We have Fx of minus 4 and minus of Fx of minus infinity is 1 by 2 minus 0 is 1 by 2, and P of minus 5 less than x less than or equal to 4 is 1 by 3, and P of minus 4 less than x less than or equal to 4 is 1 by 3, and P of 5 less than or equal to x less than 8 is 0. So, this shows that the mapping from discrete sample space to the discrete point on the real line. So, the corresponding win or loss explained. Now, another example, in a telephone call occurs at random 6 p.m. and 8 p.m. depending on the interval of arrival, the win or loss in the table shown. We have to find a cumulative density function and a probability density function. Since the phone call is uniformly distributed into 120 minutes, therefore, the probability of phone call in the region of except 0 at x is given by x is divides 120. So, the outline of the example 5.21 taken into account. So, the mapping also shown in the figure 5.24. So, the mapping in the form of real line R to R. So, from the mapping diagram, x less than or equal to minus 4 and x lies between minus 4 to 2 and 2 less than x less than or equal to 6 and d is x greater than 6. Now, we have a third steps. Check x less than or equal to minus 4, there is a no point of the map. Minus 4 less than x less than or equal to 2, fx of x is 60 by 120 because we have a distributed 120 and then the maximum possibility is 60, therefore 60 by 120 is 1 by 2 and between the interval 2 and 6 we have 5 by 8 because of the maps is 45 minutes, 45 minutes 75 by 120, therefore 5 by 8 and for x greater than 6 is 120 is given, therefore 120 by 120 is 1. So, the answer is directly coming if you know the data of the distributed 60 minutes, 45 minutes, 30 minutes and 120 minutes we can directly apply it, you can get the solution to the problem of cumulative density function. So, we can write the cumulative density function 1 by 2 into u of x plus 4, 1 by 8 into u of x minus 2 and 3 by 8 into u of x minus 6. So, that picture is shown in 5.25 the next page and the PDF is obtained from the differentiating the function f of x at the above. So, we have fx of x is 1 by 2 into x plus 4, 1 by 8 into delta x minus 2, 3 by 8 into delta of x minus 6 and corresponding graph is mapped. So, this is the graph corresponding to map and it shows that the sample space of the continuous whereas the range space is discrete and the random variable takes the discrete values and corresponding the discrete random variable x prime. So, another example, a telephone call occurs at a random between 6 p.m. to 8 p.m. So, we have a fx cumulative density function, probability density function. So, we have a continuous mapping from the real line to the real line and see the mapping diagram of figure. From the mapping diagram region shows x is negative and equal to 0 and x lies between 0 to 120, x is more than 120 and if it is infinity ray minus infinity less than n less than or equal to x. So, these are all the possibilities of the mapping. Suppose if x is less than or equal to 0 then obviously there is a no point because it is negative, there is no negative in the probability, therefore fx of x equal to 0 in the cumulative density function. Whereas if lies between 0 to 120 the uniform distributed interval is fx of x is x by 120, you take an x what value of the range from 0 to 120, substitute it you can get it. Suppose x is greater than 120, maximum is 1 only, therefore fx of x is 1. Therefore, the cumulative density function is grabbed corresponding the graph. Generally, the function can be defined in the PDF, that is probability density function. Simply differentiate fx of x equal to x of x by 120, differentiate, therefore 1 by 120 will come. So, x ranges from this. So, from here to here we can calculate it. So, this can be sketched in the figure 5.29. So, this is the graph corresponding to this from cumulative density function to probability density function.